Everybody. Happy Tuesday to all of you. Hopefully, the week is off to a good start. Um, I've been looking at the calendar and all of the different topics we need to do, and all the different topics we have done already. And I think we can afford to slow down a little bit today and just make sure that we're doing okay with all the different things. So, with my video and notes today, I would just planned on going through just all the different things. Well, maybe not all of them, but the significant things that we've been talking about, and then just a couple of practice questions to help you with the short review assignment tonight, or maybe tomorrow night for those of you who procrastinate a little bit. Um, so really quickly, circles, 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 circles. If I have a circle and there's an angle at the center, a central angle, then the intercepted arc is the same measure. Nice and easy. As long as that point is on the center, this angle is the same as the measure of that arc. But if I have an inscribed angle, which means an angle with the vertex somewhere on the circle, then the measure of the angle is half of the measure of that intercepted arc. So the diagram you see here, I've got 52 degrees for arc CD. And so angle DEC or angle CGD both have a measure of 26 because both of those are inscribed angles. And the same would be true for any angle that has this 52 degrees as the intercepted arc. So for a quick example of this, if I have a diagram that looks like this and I want you to find a whole bunch of different angles, let's see, I'll just draw these in here. If point C is the center of the circle, well then if arc AB is 96 degrees, then this angle must be 96 degrees also, angle BCA. And then the same thing down here, if this angle is 58 degrees, then this angle must be 58 degrees. But I can go farther on this one and say that I've also got an inscribed angle over here. This inscribed angle is going to be half of the measure of the intercepted arc. So half of 58 degrees, this angle will be 29 degrees. Now, it's a little bit tricky to read. Let's make that 9 more clear. All right. Then we've got all kinds of facts about triangles, including the fact that if this is a triangle that's inscribed in a circle, if this point is the center, that means segment BC is a radius, and so is segment CD, which means that triangle BCD is an isosceles triangle, which means if angle CBD is 29 degrees, then angle BDC must also be 29 degrees. And then if I've got two angles of a triangle, I could find the third angle of this triangle. This angle plus 29 must add up to 180. Or maybe you noticed that these two angles are a linear pair. So if this angle out here, FCD, is 58 degrees, then this angle, angle C, I'm going to move my C for now, that angle must be 180 minus 58 degrees, or 180 minus 29 minus 29 to find what is left, and that is 122 degrees. And if this angle is 122 degrees, that means this arc is 122 degrees because that is a central angle. Let's see, moving right along over to the other side, I've got the same relationship between the radii of this circle. BC is a radius, AC is as well. And so if this angle is 96 degrees, these two angles would have to be equal to each other. And so maybe I would do 96 subtracted from 180. Find that that is, let's see, that would be 84 degrees. And so these two angles, CAB and CBA, add up to 84, and they have to be the same. Let's take half of 84 to get 42. So this angle must be 42 degrees, and so is angle CBA. And then there's a few different things we could do. I noticed that angle ABE is an inscribed angle, which means this intercepted arc must be twice as big as 42. That must be 84 degrees. Or maybe you notice that these two angles are a linear pair, so 180 minus 96 would give you 84 degrees in here. Either one that you found would be able to find the other one because that is a central angle. And I think I'm looking at everything. I think we found all of the missing angles and arcs. So a lot of different ideas at play: triangles, isosceles triangles, um, central angles, inscribed angles, all kinds of good stuff there. Then we moved on and looked at when we have chords intersecting inside of circles. And the first, I called these the big deal ideas. We've got 5 of these to look at. Big deal idea number 1 says, if two chords intersect each other, then the product of their parts is equal. A times B equals C times D. That's big deal idea number 1. Big deal idea number 2 says that if I've got a radius to a circle, that bisects a chord, that cuts it exactly in half, that means that it must be perpendicular. Or we can go backwards. If a radius is perpendicular to a chord, then it must cut it perfectly in half. It must bisect it. Big deal idea number 3 says that if I have a line that is tangent to a curve, it must be perpendicular to the radius that is tangent at that point. And of course, you guys did lots of examples of these if you've been keeping up on the homework. I think this assignment was called Secants and Tangents of Chords or something like that, but I forget what day it is. But there were lots of examples in those notes, and certainly examples for you to try in the homework assignment. Big deal idea number 4, we're getting more recent now, says that if I've got an angle inside here, and by the way, both of these angles are the same, and if I look at the intercepted arc of those angles, notice this intersection point is not in the center, but we can still figure out how big this angle is by taking the average of the two intercepted arcs. And to take the average of two things, add them up and divide by 2. So angle A plus angle B divided by 2, that gives you the measure of both of these. These, of course, are the same because they're vertical. And then finally, big deal idea number 5 is similar, but now my point of intersection is outside of the circle, but I can still find how big this angle is by taking, instead of the sum of the two intercepted arcs divided by 2, I'll take the difference. Take one minus the other, arc A and arc B, subtract them, divide by 2. So if it's inside the circle, add them up, divide by 2. If the intersection is outside the circle, subtract and divide by 2. And I only have one example to go through, but this example is going to cover a lot of the stuff from those big deal ideas. So I've got a diagram that looks like this, and you'll have a similar diagram in your notes or in your homework assignment tonight. And I will ask specifically for different angles and arcs. For this one, I'm just going to say, let's find them all. We have enough information here. We should be able to find all of the missing angles and arcs. So here we go. First, I'm going to look for the easy stuff. Vertical angles, linear pairs. We've been doing that since September. If this angle over here, angle WTX, is 78, then angle ZTY must be 78 degrees also. These two angles form a linear pair, so 180 minus 78 gives me 102 degrees. Or these two angles form a linear pair, or these two angles form a linear pair. This angle out here must be 102 degrees also. So lots of stuff we can find without using anything that we learned in this chapter. Next thing I noticed is that because this 102 angle doesn't match up with this arc, that means point T must not be on the center. And that's okay, that just means we won't be able to use central angles. So instead, I'm going to notice that since I've got this angle here with this 102, that is an angle by a set of chords intersecting inside of the circle, since this is 102, and I know that this intercepted arc is 89, I can use that to find arc ZW, the other intercepted arc of this angle ZTW here. And actually, as I'm looking at this, I'm noticing that since I've got 78 degrees here, and this intercepted arc We could also find arc ZY doing the same thing. That's not what I did, but we could have done that as well. So since this intersection is inside the circle, I'll say that this angle, 102 degrees, is equal to the sum of these two arcs. Notice that it's arc ZW because that is where the arc or the angle is intercepting the circle. So all the way from Z to W is the one that I'm going to be able to find. So 102 equals 89 degrees plus whatever this is divided by 2. It's the average of the two. A little bit of algebra. I'll multiply both sides by 2 because multiplying by 2 and dividing by 2 will cancel out. And then I will subtract 89 from both sides because 89 minus 89 will go away. And I'm left with arc ZW is 115. Then, if arc ZW is 115, and this little arc right here, VW, is only 12, I can take 115. Whoops, that should be 115 there. 115 minus 12, and that'll leave us with 103. So this arc must be 103 degrees. All right, moving right along, the next thing I notice is that on this circle, I've got a whole bunch of arcs, and I know all of them except for one. The only one that I'm missing is arc ZY. So I'll use the fact that all the way around the circle has to be 360 degrees, and I'll take 360 minus 103 minus 12 minus 82 minus 89, and that leaves me with 74. This angle here, this arc, I should say, arc ZY must be 74 degrees. And that was the one that we could have also found by using this this angle on the inside and these two intercepted arcs. 78 equals 82 plus 74 divided by 2. We could have found that 74 by doing that also. And as we're doing this problem, I find more and more and more ways of finding different things, but I'll stick with the plan that I had coming in. Let's see, next we know that arc VX, so arc VX, that's this big arc right here, 12 plus 82. I notice that I've got an inscribed angle over here. Angle XZV is an inscribed angle with an intercepted arc of 94 degrees, which means that angle must be half of 94 degrees. Oops, half of 94 degrees is 47 degrees. So I'm just again, taking this intercepted arc, 82 and 112, or excuse me, 82 and 12 is 94, and then half of that is 47. And then finally, the only thing I have left to find is this angle out here, and I've got a couple of ways that I can find that. I'm going to pause just a moment, let you think about how you would find angle ZUY, this angle out here. And I'm not going to pause very long because if you want more time to think about this, you can pause the video, but I'm going to show you both of them. One is that I noticed that in this triangle, I've got three angles, of course, angle Z over here, angle ZTU down here, and angle VUW over there. And so since I know this one's 47 and this one's 102, I'll just do 180 minus 47 minus 102 and find the remaining angle is 31 degrees. That's one way that I could find that this angle out here is 31 degrees. Or I can notice that this angle has two intercepted arcs on the circle. The angle is outside of the circle. So I can say that this angle, angle ZUT, must be equal to half of the difference between the intercepted arcs. 74 degrees minus 12 degrees is 62 degrees, and half of 62 degrees is also 31 degrees. Those were the ways that I saw to find this. There may even be other ways that I didn't notice. And there's certainly other ways to go through this entire process. Once we get started, there's lots of ways to go about it. So there we go. I will stop at that point. There is a question on the review that asks you about finding the exact area of a sector. Don't worry about that problem. That is something that if we had more time together, we could talk about, but well, we don't. So don't worry about that question about the exact area. You can just skip that one. Otherwise, everything else should go pretty smoothly, pretty similar to what I did today. So we will pick it up again on Thursday, looking at circle equations that we haven't seen before. Hope you have a great night, and we will see you on Thursday. Bye bye.